This is Algebra 2 with Trig, Unit 1B.3. We're graphing quadratics in standard form. What we've learned in the past is that y equals ax minus h squared plus k. That is our vertex form. That tells us what the vertex is. The h and k is our vertex. Intercept form, which is ax minus p, x minus q. The p and the q are the x-intercepts. That's where the graph crosses the x-axis. We can't see the vertex just by looking at the equation. You can calculate it, but you can't see it. The vertex form shows you the vertex, but doesn't show you the x-intercepts. Standard form, ax squared plus bx plus c, that does not show you the vertex. That does not show you the x-intercepts. But it does show you a c value, which is your y-intercept. When x is 0, you're left with c. So that would give you where the graph crosses the y-axis. So the first thing we're going to look at are what's happening with a intercept form and how can we turn that into a standard form. So we're just using our math skills. We're just going to multiply. So we're going to take these parentheses and we're going to calculate it together so we don't have any parentheses. So we're going to wait for the 3. There's a few things we could do. We could distribute that 3 into the first parentheses or into the second, but not into both. But what we're going to look at first is the idea of FOIL. FOIL is front, out, inner, last. So that's when we multiply the front portion of both of these binomials. X times x is x squared. X times negative 5 is negative 5x. Two times x, which would be the inner. Those are the two inner portions. The x and the 5 were the outer. The 2 and the x are the inner. That would give you 2x. And then the 2 times 5, which is the last, 2 times negative 5 gives you negative 10. If the idea of FOIL is a little confusing, you could just think about it as the x multiplies both of the values in the other parentheses, and then the 2 multiplies both values in the other parentheses. We would collect like terms. So we get x squared minus 3x minus 10. Then we have the 3 sitting on the outside. When the 3 is sitting on the outside, we can distribute that in to get 3x squared minus 9x minus 30. So that is our equation. If you would take that equation and if you would type in your first equation into your calculator and graph it, you could see that it's going to land on our graph. By looking at the table, we can look down to see what's the smallest value that y becomes, and it looks like it's negative 36. So if it's negative 36, we can go to window to our minimum values and go to something smaller, even farther away from negative 36. You could say negative 40, you could say negative 45. I chose negative 50, and there's our graph. Now we can see the whole thing. If we want to graph a second equation right on that, 3x squared minus 9x minus 30. Now we're typing in this other equation. You could arrow over to your line and hit enter once, and you'll see that we changed that line to a bolded. Well, you can't see that. We changed the line to a bolded line. So when we graph it, it's going to be darker. Bolded. See how that worked out? So that's implying that they are right on top. It's the same equation. When we look at the table, we'll see that the values are exactly the same. So the table's the same, the graphs are the same, the equations look different. They look different, but they produce the same graph. They would produce the same table. So we're going to come over here looking at vertex form, and we're going to convert this to standard form. So think about what you would do here. There are some errors that happen in this format. When we look at our standard form, or this isn't standard form, this is vertex form, we want to make it standard form. A common mistake are people that distribute this square in and call it x squared plus 4. That is not accurate. We're going to take our f of x, and because this quantity is squared, we are going to write it twice. There's x plus 2 and x plus 2. Now it's similar to our intercept form, where we need to FOIL this. X and x gives us x squared. X and 2 gives us 2x. Again, 2 and x gives us 2x. And 2 and 2 make 4. Now, just because the 8 and the 4 are near each other does not mean we can call that 12 yet. This is actually a need for us to collect like terms. So we have x squared plus 4x plus 4. And then the 8. Now we have to distribute the 5. Before we can get to the 8, we have to distribute the 5. That leaves us with the negative 20 and the 8 side by side. We don't need parentheses anymore. And that leaves us negative 5x squared minus 20x minus 12. Those should be the same exact equations. You could test that out by putting it into a calculator and seeing if we get the same result. So negative 5, x plus 2 squared plus 8. And our other equation was negative 5x squared minus 20x minus 12, and when we look at the tables, we see that we get the same exact values in the tables. So that helps verify that, yes, these are exactly the same. There were no mistakes. when we're looking at standard form, that's what this is. This is standard form, y equals ax squared plus bx plus c. This is a parabola. It has an axis of symmetry. To find that line that goes down the middle of the parabola, we don't have an h value. We don't know where the vertex is at. We don't even have 2 points on the same horizontal. So we can't just divide it by 2. We have to come in here and say negative b divided by 2a. That is a formula that will help calculate down the center of our parabola. That means that the negative b over 2a is going to be the x value of our vertex. The x coordinate of the vertex is the negative b over 2a. Whatever number that calculates out to be will be the vertex. It has a y-intercept. It crosses the y-axis. When x is 0, you get a c value. At 0c, plug 0 into your equation, 0 squared times a. That gives you 0, and 0 times b gives you 0. So when you plug 0 in for x, you get the c value every time. And then we already know about how this opens. It will be up if a is greater than 0. The graph opens upwards if the a value is positive. If the a value is less than 0 or negative, it's going to open down. So that leads us to this idea of a maximum and minimum values, which we've already talked about in our other lessons, that we have a minimum value when the a is positive, you have a maximum value when your a is negative. It opens downwards, you have a high point. It opens upwards, you have a low point. So we're going to look at this equation. Let's actually start with this second one. It comes out, I think, a little bit cleaner, and then we'll try the tougher one. All right, we'll try this one first. Tell whether the function has a minimum or a maximum. So you have to think about what part of the equation gives us this hint. What are we looking at to help us decide that? The c value is going to tell us where it crosses the y-axis, but which direction it opens, if it's a minimum value or a maximum value, is all about how it opens. So if the a value, in this case, is less than 0, then I know I'm going to have a maximum value. And for us to calculate what this maximum value is, I'm going to use x equals negative b over 2a. So my b value is 12, so negative 12 over 2 times a, which is negative 3. I can look at my equation and I can see that the a value is the negative 3 and the b value is the 12. The formula is negative b, so it turns out to be a negative 12 divided by a negative 6. which gives us a positive 2. Now that's just the line of symmetry. The vertex is on the line of symmetry. So negative 3 times 2 squared plus 12 times 2 minus 6. We plug that line of symmetry back into the original equation. And then we have to simplify. Now do be careful. This is not negative 3 times 2 squared. This is 2 squared times negative 3. There's a difference. So negative 3 times 4 plus 24 minus 6. This is going to be negative 12 plus 24. That gives me 12. Minus 6 more gives me 6. So my vertex is 2, 6. And my maximum value is y equals 6. Okay, we'll slide over here to this other one. We look here and we see that the a value is greater than 0. That means the graph is going to be opening upwards. So that means it's going to have a minimum value. It has a low point. We use our line of symmetry, negative b over 2a, negative 6, because the b value is negative, so it's negative of a negative, which is going to turn positive, over 2a. So this becomes 6 over 4, which is 3/2.
I just wrote 1.5. Is that okay?
1.5 can work. When I start squaring 1.5 and timesing it to values, sometimes a fraction's a little bit easier to work with. Our y value is 2 times 3/2, and we square it, minus 6 times 3/2, plus 8. So we substitute in that 3 over 2 into our original problem. And we'll square our parentheses. So it's 2 times, and when you square a fraction, you multiply the top by itself, you multiply the bottom by itself. So that's 9/4. 3 times 3 is 9, 2 times 2 is 4. When you multiply a fraction, you multiply the tops of the fraction. So minus 18/2 plus 8. That's a little crazy looking. Can any of that be simplified? Well, some people look here and you might say 18/4. That could work, or you might divide out or simplify. So you have 9/2 minus 18/2 plus 8. So that's negative 9/2. Negative 9/2 because they have common denominators. How can I make this have common denominators? This is a number 18. I've got to add it to my negative 9/2. So that's got to be 16/2. 16 divided by 2. Now they both have common denominators. They're kind of like terms now. So my y value is going to be 7/2. My vertex is 3 over 2 and 7 over 2. 1.5 and 3.5 if you're a decimal one. So this has a minimum at y equals 7/2, or 3.5. That was a little trickier with all the fractions. We dealt with fractions in yesterday's lesson also. On the flip side, we have a couple questions to think about. So what we're going to consider here is an equation that looks like that, 5x squared minus 7. What form is the equation in? Does anyone want to share? Standard. You could call this standard form if you want. Standard form. Y equals, or f of x, I guess, 5x squared minus 7. The a value is the 5, the b value is not written, and the c value is the negative 7. That can totally work. So you could consider that standard form. But what's also kind of neat about this, as long as we don't have a b value, you could call this vertex form. Where we call this 5 times x minus nothing squared minus 7. Where your a value is still 5, your h value is 0, and your k value is negative 7. You've got the same exact equation. So we're supposed to identify what the vertex is. Well, in this case, we have our parent function, and we stretch it by a multiple of 5, and we translate it down 7. So we have a vertex at 0, negative 7. We could also look at vertex form and see 0, negative 7. So we're going to get this vertex to be the same. In our comparisons, there is no reflection, but we have a vertical stretch by a scale factor of 5. That's what's happening compared to the parent function. And then this is translated . 7 units down. So that's our process of comparing our two graphs. Any graph with the parent function. Okay, our last one here. What form would you call this one in? All right, most of us might call this standard form. So we have our f of x, we have our x squared, we have our minus 4x, our a value is 1, our b value is negative 4, and our c value is 0. So that would be our standard form. All right, what this is telling us is that our y-intercept must be at the origin because there is no c value. So when x is 0, y is 0. Now, could this equation be written any differently? Well, don't they both have an x in it? They both have an x in it, so I could factor out what they both have in common. It's called the GCF. We'll be doing that even more in the future. But earlier today, we spent some time distributing in. Well, this is the same thing, but taking it out. Now, when we look into this form, it does look a little bit like x minus nothing and x minus 4. This looks like intercept form, which has a 0 for an intercept and 4 for an intercept, where your p is 0 and the q is 4. This would be intercept form. So sometimes you can convert things around. We'll talk more about turning standard form into intercept form. That's all the factoring units that we'll do in the future.